You know, it's funny. We take our eyes so completely for granted. I mean, think about it. You wake up, you see the alarm clock, you see the floor, you navigate the hallway to the bathroom without crashing into the wall. It's just effortless.
It really is. It's one of the most complex systems in nature, for sure. And for decades, computer scientists looked at that miracle and thought, well, how hard can it be to teach a machine to do that?
Turns out, pretty hard.
Incredibly hard. But here's the thing. We aren't just, imagining a world where machines can see anymore. We're living in it. We have cars that read traffic signs, phones that unlock by scanning the geometry of your face.
And algorithms that can spot a tumor on an X-ray faster than a human doctor. And that is exactly what we're unpacking today. We've got this massive stack of research here covering the current state of computer vision. We're going to look at the mechanics of how a machine translates a grid of numbers into sight, how that technology has evolved into generative AI that can, well, dream, and the messy ethical spiderweb we're all currently stuck in.
It's a fascinating evolution. We're really witnessing a move from analysis cell machines understanding the world to synthesis.
To machines creating new worlds.
Exactly.
So let's start at the absolute bottom, the atomic level of digital sight, the pixel.
So to you and me, a picture is a memory. It's a sunset, a dog, a birthday party. To a computer, a picture is just a spreadsheet.
I love that analogy from the notes. It says if you strip away the interface, an image is just this massive grid of numbers.
That's it. Let's take a standard digital photo. It's a mosaic of these tiny squares called pixels. If it's a black and white photo, every single pixel gets a number between 0 and 255.
So 0 is pitch black.
And 255 is pure white.
So a computer doesn't see a shadow or light. It just sees a cluster of zeros and tens next to a cluster of, say, 200s.
Precisely. And when you add color, the math triples. You're dealing with RGB red, green, blue. Now, every pixel isn't just one number, it's 3. It's like a three-dimensional stack of matrices.
And wait, there's a fourth layer too, isn't there? The alpha channel.
Yes, often there is. The alpha channel dictates transparency. It tells the computer how see-through that pixel should be. So when we talk about computer vision, we aren't talking about eyes. We're talking about an algorithm that can ingest this massive multi-dimensional array of millions of numbers and find patterns in that noise.
Which brings us to a really foundational concept in the research. David Marr. This goes way back to the 70s and 80s, right?
The MIT neuroscientist, yes.
Yeah.
His work is, it's still the blueprint for how we think about this. Marr argued that you can't just throw hardware at the problem. You have to understand vision in layers. He used a baking analogy that I think is still the best way to visualize it.
Okay, I'll set it up. He proposed 3 levels. The first is the computational level.
That's the what and the why. So if you're baking a cake, deciding what kind of cake you want and why you're making it, in vision, it's the goal. I want to recognize a face or I want to spot a red light.
Okay, and then comes the algorithmic level.
That's the recipe, the representation. How do we take the input, the ingredients, and process them? What are the steps?
Right.
In our case, this is the software, the actual code and math that processes those pixel values we just talked about.
And finally, the hardware implementation.
That's putting the cake in the oven. This is the physical machinery.
Yeah.
In your brain, it's neurons and synapses firing. In a computer, and specifically for vision, we're usually talking about GPUs, graphics processing units.
Because they can handle all that heavy lifting.
Well, because they can do parallel processing. Remember, an image is millions of numbers. A standard CPU, it handles tasks one by one, very fast.
Right.
A GPU can crunch thousands of those numbers simultaneously. It's the difference between one chef cutting carrots very quickly and 1,000 chefs cutting carrots at the same time. That hardware layer is what finally allowed the algorithmic layer to catch up to the computational theory.
Okay, so we have the hardware chefs, but how do they actually recognize an object? The research talks about feature extraction. This feels like the secret sauce.
It is. A computer doesn't look at a photo of a car and just say, that's a car, immediately. It breaks it down. It looks for edges. Where does the pixel value shift suddenly from light to dark? That's a line.
Okay, so it finds lines. Simple enough.
Then it looks for how those lines connect. Do they form a circle? That might be a wheel. Do they form a rectangle? That could be a windshield. It builds a hierarchy. Low-level features like edges become mid-level features like shapes, which become high-level features like objects.
So it's almost like a checklist. 2 circles at the bottom, a metal box on top, some glass in the middle. Probability says car.
Exactly. It's probabilistic. It's never 100% sure. It's just 99.9% sure based on the millions of examples of cars it has in its training data.
But seeing a single object is one thing. Understanding a whole vibe is something else entirely. There's a section here on scene understanding that really blew my mind. The difference between just naming items and understanding what's actually happening.
Context is king here. The example in the text is a photo of a dinner at a rooftop Italian restaurant.
Right. So picture this. I snap a photo. There's a charcuterie board, a wine glass, a sunset, and a city skyline in the back.
To a basic object detector, that's just a list. Cheese, cracker, glass, building, sky. That's boring. That's not vision.
That's just inventory.
That's it. It's inventory. Real vision, according to the breakdown here, requires 4 steps.
Okay.
Step 1 is that object detection we just discussed, so we know what items are there. Step 2 is spatial understanding. The AI has to understand the 3D geometry from a 2D image. It knows the food is on the table. It knows the glass wall is behind the table, and the skyline is miles behind that.
It's building a mental map of depth.
Correct. Step 3 is activity recognition. It looks at the arrangement. The wine glass is full, the food is plated. This isn't cooking, isn't cleaning. It is dining.
And the final piece.
Context recognition. This is the Sherlock Holmes moment. It combines everything. Rooftop view, plus fancy plating, plus wine, plus evening light. It all equals romantic dinner, or maybe special occasion at an upscale urban venue.
It's inferring the narrative, not just listing the data. That is wild.
And that is the bridge to where we're going next. Because if a computer can understand the components of a narrative image, well, it can also learn to assemble them.
Generative AI. We are moving from the eye to the imagination.
From perception to creation. This is the biggest shift in the field in, the last 5 years. We aren't just teaching computers to see, we're teaching them to visualize.
The notes mention generative fill as the perfect example of this. So let's say I have a photo of an astronaut on Mars. The ground is that classic reddish-pink rocky texture, but the framing is bad. It's cropped too tight. I want to zoom out.
Right. In the old days, you'd have to paint that in by hand, pixel by pixel. A lot of work. Now, the AI looks at the pixels on the edge of the frame. It analyzes the statistical distribution of the colors and textures, and it asks mathematically what is most likely to come next.
It hallucinates the rest of the landscape.
Hallucination is actually the right technical word here, yeah. It generates a mountain range that doesn't exist, or a moon that wasn't there, but it fits the mathematical pattern of Mars.
So how is it doing that? Is it just cutting and pasting from other pictures of Mars it found on Google Images?
No, and that's a really common misconception. It's not a collage, it's not cutting and pasting. It uses something called diffusion models.
Okay.
Think of it like this. Imagine taking a clear photo and slowly adding static noise until it's just gray snow. You've destroyed the image.
Okay, I can picture that. Just pure TV static.
The AI is trained to do that process in reverse. It looks at the static and learns how to remove the noise to reveal the image. It learns the pathways from chaos to order. So when you ask it to generate Mars, it starts with digital static and refines it step by step, guessing and checking until a Mars landscape emerges.
That is wild. It's sculpting with static.
That's a beautiful way to put it.
Yeah.
And because it's probabilistic, you can guide that sculpting with language.
The prompt. This was my favorite part of the reading. The jellyfish sofa.
Ah, yes. This is an actual test case in Adobe Firefly, wasn't it?
It was, and the prompt was incredibly specific. Sofa made of alkaline batteries with a lighted lampshade next to it in the shape of a jellyfish.
Which is just absurd. No such object exists in the training data. The AI has never seen a photo of a battery sofa, but it understands the concept of sofa and the texture of batteries, and it fuses them.
But they didn't stop there. They used generative fill to edit it. They highlighted the background and typed, "Add jellyfish teal retro wallpaper." And then, and this is the kicker, they added a cute gray French bulldog.
And the dog didn't just look like a sticker pasted on top, I'm guessing.
No. The lighting on the dog's fur matched the blue light coming from the jellyfish lamp.
So that is the spatial understanding we talked about earlier, but now it's applying to creation. The AI understands the light sources in this synthetic scene and renders the new object to match the physics of that world.
It knows if the light is blue, and from the left, the dog's right side should be in shadow.
Exactly.
But that doesn't just happen by magic. The source material really emphasizes that we're entering an era of prompt engineering, garbage in, garbage out.
Or vague in, vague out.
Yeah.
If you just type cool dog, you get a generic image.
The research lists 6 core components for a high-quality prompt. It's basically a checklist for communicating with the model.
Let's run through them quickly because I think this is practical advice for anyone listening who wants to play with these tools. First is action.
Right. What is the AI doing? Is it sketching, rendering,
Yeah.
Carving. If you tell it to carve, it'll simulate the texture of wood or stone. If you say crochet, it'll look like yarn. Second is subject. Be specific. Don't say dragon. Say cybernetic dragon with iridescent scales.
Third is style. This is a huge one. You can ask for photorealism, abstract, or something called style transfer. You can say, make this look like a painting by Gustav Klimt.
And suddenly your photo has gold leaf and geometric patterns.
Exactly. You're borrowing the mathematical aesthetic of an artist. Fourth is scene so, lighting and weather, golden hour, or cyberpunk neon. Fifth is color palette. And finally, technical specs. You can actually ask for camera lenses, shot on a 35mm lens with f1.8 aperture.
And the AI mimics the depth of field of that specific camera lens.
It simulates the blur, the bokeh perfectly. It knows how that specific glass distorts light.
That's incredible. But let's ground this again. We've talked about art and hallucinations and battery sofas, but computer vision is also doing some heavy lifting in the real world, the utility side of things.
Right. We have to talk about reverse image search. Tools like Google Gemini or Amazon Lens. This is really bridging the digital and physical worlds.
The blueberry dessert example resonated with me because I cook. You see a photo on a food blog, it looks delicious. There's no recipe, just a picture.
So frustrating.
Usually, yes. But you upload that screenshot to the AI. It analyzes the visual data, the crust texture, the shape of the berries, the glaze. It identifies it as blueberry cheesecake bars, and then it fetches a recipe.
And think about the back end of that. It connects the image to information. It's converting that image into a mathematical vector, finding other images in that same vector space, and then linking you to the text associated with them.
It's not just for food, though. The industry applications are massive.
Agriculture is a big one. A farmer can snap a photo of a leaf on a soybean plant. The AI detects these subtle discoloration patterns, tiny shifts in the pixel values that indicate a specific fungal disease before a human eye would even notice it.
Or healthcare. We mentioned tumors earlier.
Yeah, radiologists are using this as a second pair of eyes. It's not replacing the doctor, it's highlighting the anomaly. Hey, look at this cluster of pixels here. It just reduces the rate of misdiagnoses.
Or retail. I've done this. I saw a cool lamp in a hotel lobby, took a picture, and Amazon Lens found the exact manufacturer in like 2 seconds.
It turns the physical world into a search bar. It's incredibly powerful.
However, and this is the deep dive turning point, we cannot talk about this technology without talking about the cost, the ethical frontier.
Two rights and a wrong. That's the tension described in the chapter.
So let's start with copyright. Because those diffusion models we love, the ones making the battery sofas, they learned how to do that by looking at billions of images scraped from the internet.
And they mostly didn't ask for permission. This is the core conflict. On one side, you have the right to technological innovation. On the other, artists have a right to their work. If an AI studies 1,000 paintings by a living artist and then can generate new work in their exact style, is that theft?
The legal term is substantial similarity.
Right. And copyright usually protects the specific expression of an idea, not the style. If I paint like Van Gogh, that's not illegal. But AI, it just blurs that line completely.
So the law is struggling to catch up.
It really is. Now, the source does mention that Shutterstock is trying to find a middle ground.
Right, with the contributory fund.
Yeah. If your photos are in the data set used to train the model, you get paid. It treats creativity like a raw material like oil or lumber. You get paid for the resource you provide.
But it's not just about money, it's about truth. And this brings us to the bias issue. The notes discuss the Google Gemini overcorrection incident. This was, well, it was awkward.
It was a significant stumble, for sure. We know AI models can be biased because they're trained on human data, and our history is, unfortunately, biased. If you ask a standard model for a CEO, it historically shows you white men because that's what the training data contains.
So the engineers tried to fix that.
They did. They injected diversity instructions into the prompt processing, but they over-indexed. So when users asked for a historically accurate image of a 1943 German soldier, a Nazi, the AI, tried to be diverse, generated images of Asian and Black Nazi soldiers.
Which is historically impossible.
It erased the reality of history in an attempt to be inclusive. It shows that fixing AI isn't just about flipping a switch. It requires a nuance that, frankly, machines just don't have yet.
It's a reminder that these systems don't know history. They just follow rules.
Exactly. They are prediction engines, not truth engines. And that's a distinction we have to keep in mind.
We can't leave the ethics section purely on the dark side, though, because there is a section here on assistive technology that is genuinely moving.
This is the bloom amidst the doom. For the visually impaired community, computer vision is revolutionary.
The Seeing AI app.
Yes. I mean, imagine being blind and holding your phone up to a pill bottle. The AI reads the label atorvastatin, 20 milligram,
Yeah.
and speaks it to you. Or pointing it at a menu or a friend's face to know if they're smiling.
It's providing independence, privacy. You don't have to ask a stranger, what is this medicine?
Or consider lip-reading tech for the hearing impaired. The AI tracks the micro movements of the lips and generates captions in real time. It's using that detailed feature extraction we talked about to bridge a communication gap.
It really delivers on the promise of the technology. It's not just making cool art, it's making the world more accessible.
It is the best possible use case for seeing understanding.
So let's look back at the map we've drawn today. We started with the pixel, the raw numbers, 0 to 255. We walked through David Marr's kitchen to bake the cake of vision.
We saw how machines learn to classify dinner plates and analyze the geometry of a room using spatial understanding.
We watched them start to dream with diffusion models, creating jellyfish sofas and filling in the landscape of Mars by, reversing the static. And we faced the hard reality that this technology is scraping our creativity and struggling with our history.
I think the takeaway is that computer vision isn't some feature of the future. It is the operating system of the present. It's in your pocket, your car, your doctor's office.
And here's a final thought to chew on. It's a story from the research that we haven't resolved yet.
The State Fair Art Competition.
Right. A guy enters an art competition with a piece generated by Midjourney. He wins first place, and people are furious. But then he goes to the U.S. Copyright Office to register it.
And they denied him. They said because a human didn't execute the work, it cannot be copyrighted. It has no owner.
I mean, think about the implication of that. If an AI generates the most beautiful, moving image you have ever seen, something that makes you cry, the law says that art belongs to no one. It's just there, like the wind.
It raises the question, is creativity a uniquely human trait that requires a soul? Or is it just a very, very complex math equation?
Something to think about the next time you unlock your phone with your face. Thanks for diving in with us.
See you next time.